Hi, my name is Mohammad Dehqan. I'm a master's student at University of Waterloo, and today I will present the paper GRS Combining Generation and Revision in Unsupervised Sentence Simplification. Text simplification is a task of reducing the complexity and improving the readability of text while preserving its meaning. This is beneficial for persons with reading disabilities, non-native speakers, and people with low literacy. In this example, some parts of the complex sentence are deleted and some expressions are paraphrased to make the final sentence simpler. We can categorize text simplification approaches into generative and revision-based approaches. Generative approaches produce a simple sentence from a complex sentence in one step. However, revision-based methods iteratively edit a given sentence using a sequence of edit operations like reordering, deletion, or lexical substitution. While generative models learn complex edit operations implicitly from data, the explicit edit operations performed by revision-based approaches can provide more control and interpretability. We can also categorize text simplification approaches into supervised and unsupervised methods. Supervised methods tend to have better performance but require aligned complex simple sentence pairs. However, unsupervised methods do not use such data but do not perform as well. In GRS, we bridge the gap between generative and revision-based methods. We introduce paraphrasing as an edit operation within an iterative revision-based framework. GRS is unsupervised and combines the advantages of both generative and revision-based approaches. Actually, it is controllable and interpretable, while generative models are less interpretable and controllable. GRS can apply complex phrasal substitutions better than revision-based approaches by leveraging the paraphrasing operation. In terms of performance, GRS outperforms all previous unsupervised models on the Newsela dataset. Now I will explain the GRS model in more detail. GRS iteratively revises a given complex sentence by applying paraphrasing and deletion edit operations on sentence fragments. In each iteration, edit operations produce multiple candidate sentences, and then candidates are evaluated using a score function. The score function guides our search for best simplification using soft and hard constraints on simplicity, linguistic acceptability, and meaning preservation. We filter out those candidates that do not improve the score of the input sentence by some threshold, and then the best candidate is selected. The selected sentence acts as input to the next iteration. This process continues until none of the candidate sentences can pass the filters. In the following slides, I will explain the edit operations in more detail. The deletion operation is composed of removal and extraction suboperations and generates multiple candidate sentences in each iteration. Using the parse tree of the input sentence, we obtain all constituents from different depths of the parse tree. Then the removal suboperation creates new candidate sentences by removing each of these constituents, and the extraction suboperation selects each of these constituents as a candidate sentence. We use a BART model fine-tuned on a small paraphrasing dataset as the paraphrasing model. During inference, we use lexically constrained decoding to force the paraphrasing model not to generate the negative constraints, which are complex words in the input sentence. The negative constraints are selected by the complex component detector. We devised the complex component detector to reduce the number of times calling the paraphrasing model. Instead of calling the paraphrasing model multiple times, given different set of negative constraints, we use the complex component detector to find the correct negative constraints and call the paraphrasing model once. For creating the complex component detector, we first fine-tune a pre-trained language model on two corpora with different complexity levels to obtain a complex simple classifier. We use the attention layers of the classifier to extract the complex components from a given input sentence. This image visualizes one of the attention layers of the classifier, and the attention weights are reflected by color intensity. This visualization shows that the word facilitate has received more attention than other words in the given sentence. Let's take this example. In the first iteration, one of the candidate sentences generated by the deletion operation is selected as the best sentence, and then it is given to the model again. In the second iteration, the sentence generated by the paraphrasing operation is selected, and words announcement and massive are set as negative constraints by the complex component detector. We have evaluated our model on Usalo and asset test sets using SARI and FKGL evaluation metrics. Also, we have shown that human evaluation is aligned with the automatic evaluation. On Usalo dataset, our best model outperforms previous unsupervised methods. On asset dataset, we are the second best model among unsupervised models, but we close the gap between revision-based and generative approaches. We have shown that our model is controllable and analyzed the simplification search and the complex component detector module. You can find more details of these analyses in the paper. So to conclude, we propose GRS, a controllable and interpretable method for unsupervised text simplification that combines the generative and revision-based methods and has the advantages of both approaches. Empirically, we showed that GRS outperformed state-of-the-art unsupervised methods on the Usalo dataset. Thank you for listening to this presentation.